Hello again, and welcome back to another episode of the CCQTA Lunch and Learn series. I'm Dave Murray, Secretary to the CCQTA. This is our second episode on vapor pressure, with a focus on sampling and the impact sampling may have on vapor pressure measurement. In this episode, we're going to focus on two areas: sampling methods and testing methods. Now, before we get into these, let's roll back to a couple of items we talked about in episode 1 that impact both of these. First, let's do a little refresher on what we talked about in episode 1. We talked about the theory of vapor pressure, the various definitions, and how those apply to a complex mixture like crude oil. Next, we talked about all the different terminologies that are used throughout the industry, some clear and some not so clear, and why that often leads to confusion. And lastly, we talked about why vapor pressure matters. That included safety, operations, and emissions. You may remember this plot from episode 1. It compares the boiling point of methane through hexane versus the carbon number, where the size of the bubble represents the true vapor pressure of each. You can see methane has a very large vapor pressure bubble, which also means it has a very low boiling point at minus 161 degrees Celsius. Hexane, on the other hand, has a small vapor pressure bubble at a much higher boiling point at 69 degrees Celsius. Also note that the vapor pressure is well below atmospheric pressure and gets lower with each increasing carbon number. We are focusing on carbons 1 through 6 as the major contributors to vapor pressure. The orange line represents an ambient temperature of 20 degrees Celsius. You can see that C1 through C4 all have boiling points well below ambient temperature, so at atmospheric pressure they boil throughout a fluid and not just from the surface. Remember this as we get into the details of the various sampling and testing methods. Let's look at a real crude composition and how the vapor pressure is impacted by the composition. You might remember Dalton's law that the sum of partial pressures of each component make up the total pressure. On the right, you can see that C1 through C10 make up about 34% of the total mass of the sample. Let's look at the impact of this in terms of theoretical true vapor pressure, which, if you recall, is at 0:1 vapor-liquid ratio. This chart represents the composition we just looked at. As with the previous charts, the size of the bubble represents the vapor pressure contribution of each component. Comparing the concentration of C4 to C1, C1 is only a fraction of the concentration of C4, but the vapor pressure contribution is almost the same as for C4. As per Dalton's law, the vapor pressure contribution of each of these add up to the overall vapor pressure, which in this case is 85 kPa. What is also interesting is that 74 kPa comes from the C1 to C4, and only 11 kPa comes from C5+. At 20 degrees C, that means the bulk of the vapor pressure contributing components are boiling and are vulnerable to rapid loss. That is an important point as we move into the discussion on sampling. Before we get into sampling, I just want to show this matrix for determining if results should be representative of the product. This can be broken down into 3 activities and an outcome: sampling, sample handling, and finally the test method used. If all 3 are good, then the results should be representative of the material sampled. If any of these other 3 are poor, then the results are likely not representative. There's an old saying that junk in equals junk out. That is in reference to bad samples give bad results, no matter how good the handling and test method are. There are 2 basic types of sampling methods, plus 1 hybrid. Atmospheric sampling, which means sampling into a bottle, jug, or other similar container that is open to the atmosphere. And sealed sampling, which means transferring the sample directly from the sample point to a sealed container without contacting the atmosphere. And the last one is hybrid sampling, which is a combination of both sealed and atmospheric, which I'll explain in more detail later. We saw this illustration in episode 1 in relation to open or closed systems such as tanks. The same applies to sampling. Sampling into an open container exposes the sample, in this case crude oil, to atmospheric pressure and ambient temperature. The impact of that can be from negligible to significant depending on the composition of the fluid being sampled. In a scenario where there is negligible C1 through C6, the vapor pressure will be very low. Therefore, evaporation will be slow and loss will be more limited. In the opposite scenario, where C1 through C6 are prevalent or even dominant, the vapor pressure will be much higher and the evaporation loss will be much quicker. Also keep in mind that C1 through C4 boil between minus 161 degrees C and 0.5 degrees C, so they are going to be boiling out of the whole sample and not just from the surface. We'll discuss sampling techniques that have been developed to try to minimize evaporation when taking an atmospheric sample. As we've discussed, sampling has a risk of loss due to evaporation and boiling, so the first thing you must understand is the product being sampled so that appropriate sampling decisions can be made. First of all, what is the approximate product density? Low density products tend to have a high concentration of lower molecular weight components and thus also tend to have higher vapor pressures. Higher density products should be the opposite. However, keep in mind that diluted bitumen can have 15 to 30% of low density diluent as part of the overall composition. The density is a clue, but not the whole story. Next is, what is the approximate vapor pressure? The vapor pressure, if known, obviously, is the best indicator of the volatility and how the sample will behave during sampling, handling, and testing. Then, what testing is being planned or requested? The volume of sample required to conduct the test requested may influence the type of sample container and the sampling method. Some tests are less sensitive to loss than others. For example, sediment and water are macro-level tests and may not be significantly impacted by a small mass loss due to evaporation, whereas tests like vapor pressure and composition are significantly impacted by any loss by evaporation. Lastly, what type of sample point is available? If only a sample tap is available, then that limits the number of sampling methods that could be employed. These questions will help you choose the appropriate sampling method. If you don't know any of these, err on the side of caution and assume the vapor pressure is high and use the appropriate method. We will look at atmospheric or open container sampling first. Atmospheric sampling is the practice of sampling into a container that is not intended and or suitable for pressurized contents. These containers include bottles, tin cans, bigger tin cans, jet fuel type sealed containers, larger like 20-liter cans, up to even barrels. You would never sample a high-pressure product such as LPGs, which are predominantly propane or butane, into any of these containers. ASTM D4057 API MPMS Chapter 8.1 is the standard practice for manual sampling of petroleum products. This is an extensive sampling practice that covers many sampling scenarios, including bottle sampling, dip tube sampling, tank composite sampling, interface sampling, and tank bottoms. Pressurized sampling is also included in this sampling practice. However, we'll discuss that later on in more detail. The goal is to capture a sample and maintain the integrity of the sample. These are the factors that impact atmospheric sampling and can impact the integrity of the sample. Product temperature and pressure. If the product is from a high temperature source, then the vapor pressure of the material may also be high with potential for rapid loss of light ends. The same goes for a high pressure source. If the source is high pressure, the vapor pressure may also be high. However, keep in mind that the pressure may simply be from pump discharge pressure and the pressure may be independent of the product. Again, it's best to understand the product you are sampling. Ambient temperature. If the ambient temperature and thus your container temperature is higher than the product temperature, such as in a cold tank or an underground line, then the introduction to a warmer environment will increase the vapor pressure and promote evaporation and loss. Agitation. Remember that vapor pressure is a surface phenomenon, so agitating the surface by filling will promote evaporation because the surface equilibrium is constantly disturbed, and agitation also increases the surface area available to evaporate. And lastly, time. Evaporation and loss are also time dependent. If you're working with a very low flow sample point and take a significant amount of time to fill a container, then there is an opportunity for evaporation and loss. Sampling rate has to be balanced with the other factors as well, but should be kept in mind. As we just discussed, sampling techniques are intended to reduce the risk sampling poses to sample integrity. One of the parameters we are trying to prevent when sampling is agitation. Dip tube sampling picture on the left fills the sample container from the bottom, so the fluid entering the container is beneath the liquid level, so the surface is only minimally disturbed when filling. To put this in easy context, imagine filling water into a bucket from your garden hose. If you hold the hose above the liquid surface, it splashes all over your legs. If you put the hose outlet into the bucket near the bottom, the surface remains relatively calm and simply rises with the water level. The example diagram is specific to a tank with a tap. However, the same concept applies to any type of sampling situation by simply inserting your sampling outlet tube into the product while sampling. Make sure not to overfill your container and leave room for thermal expansion. And lastly, make sure to cap your sample immediately after sampling to avoid any further loss. In a scenario where the source material could be warmer than the ambient conditions, the vapor pressure of the fluid will also be higher. The goal of the sampler in this case is to cool the product to near ambient temperature to reduce the vapor pressure and minimize loss. A simple way to do this is with a sampling coil. The sampling coil is simply just a coiled length of tubing, ideally stainless, inserted in water or a water ice bath to act as a heat exchanger to cool the product as it moves from the sample point to the sample container. Just make sure your tubing is suitable for the pressure of the system. Same as with the dip tube sampling, make sure not to overfill your container and leave room for thermal expansion. And same as before, lastly, make sure you cap your sample immediately after sampling to avoid any further loss. Many sampling methods are available for many specific applications. Understanding the impact of sampling and what steps can be taken to minimize that impact will help guide you in choosing the best sampling method. It is important to understand why you are sampling and how taking the sample may have an impact. A little voice should always be at the back of your mind when planning to sample, asking, how do I minimize any light end loss? With that, let's move on to sealed sampling. Sealed sampling has less risk of exposure to atmosphere and as such less risk of loss. However, it involves more complex equipment and complicated preparation and sampling techniques. Sampling into an open container is relatively simple, as we've discussed, but has potential for sample integrity risks. Sealed sampling is the method of choice for maintaining sample integrity. However, it is more complex and requires a more skilled operator to execute properly. There are only a few factors that need to be considered when sampling into a sealed container. Since the sample will be collected under pressure, the sampling equipment and container must have a maximum allowable working pressure greater than the source pressure. This includes any valving, tubing, fittings, etc. that might be involved. Product viscosity is a second factor that impacts sealed sampling. Since the sealed sampling system uses transfer tubing, valves, fittings, etc., there are limitations on the viscosity that can pass through those items under the source pressure. This is also a function of the viscosity at the source temperature versus the viscosity of the temperature for the container. For example, if you attempt to sample hot bitumen at 100 degrees Celsius into a conventional cylinder at room temperature, the bitumen likely may solidify in the tubing en route to the cylinder, therefore no sample gets collected. In that same scenario, if the cylinder is filled with hot bitumen, it will cool and solidify in the cylinder en route to the lab, making it very difficult for them to handle. This is just one more reason to understand what purpose samples are being collected for to adjust sampling and handling methods accordingly. Lastly, thermal expansion and ullage are very important factors for sealed sampling. Ullage is simply the space provided inside the container to allow thermal expansion of the product. Unlike gases, crude oils are incompressible, so when thermal expansion occurs without sufficient space, the container becomes liquid locked, and the pressure rises exponentially. A liquid locked container can quickly exceed the maximum working pressure and potentially result in a rupture or rapid release. Types of sealed sampling containers. These are the four most commonly used types of sealed sampling containers. The floating piston cylinder, or FPC, has a piston isolating the pre-charge chamber from the sample chamber. There are gauges on either end to monitor the pressure, and there's typically a fill gauge which is either magnetically or mechanically coupled to the piston to identify the fill level. The pre-charge chamber is filled with an inert gas such as nitrogen, argon, or helium, etc. This is used to provide back pressure to maintain the product in the sample container in a single-phase state throughout handling. The traditional constant volume cylinder, or CVC, is also sometimes referred to as a sample bomb. It is simply an open chamber with sealing valves on both ends. These are commonly used for gas sampling. The CVC with the dip tube as pictured is intended for liquid sampling with a displacement fluid such as water or glycol. The displacement fluid is immiscible in hydrocarbon and acts similarly to a piston where the product slowly displaces the displacement fluid as the cylinder fills. I'll get into more detail on how this works in a little bit. Lastly, the manual piston cylinder, or MPC, is effectively the same as an FPC in that it has an internal piston isolating the product from an inert gas. The difference is that the piston is also connected to a handle which allows the piston to be operated manually as opposed to relying on differential pressure to move. These are very useful for low pressure sample points such as tanks where only the head pressure of the tank contents is available. This pressure can be less than 150 kPa or 20 psi, which can make sampling either very slow or impossible with an FPC. There are three options for sampling with a constant volume cylinder. Let's look at the difference between these three and how it may impact the sampling collected and subsequent analysis. This is an illustration of how an evacuated CVC is used during sampling. There are a couple of issues with this sampling method. Firstly, the product must have sufficient vapor pressure to generate a vapor space and displace a portion of the oil. That means the bubble point must be greater than atmospheric pressure. For stabilized crudes, this often means opening the bottom valve and nothing or very little comes out, let alone enough volume for thermal expansion. This puts the cylinder in a potentially liquid lock scenario with potential for overpressure and rupture. In production environments such as a gas plant or wellhead, the vapor pressure is likely high enough to allow a vapor space to be generated. Secondly, if there was sufficient vapor pressure to displace enough liquid, the sample had to be in two phases, gas and liquid, and some of the liquid had to be removed. This is an example of the impact of removing one phase preferentially over another. Keep in mind the values used are just for illustrative purposes. Say a CVC starts full of crude oil with a 4:1 gas-oil ratio. To create ullage space, part of the liquid must be removed to lower the pressure and create a two-phase environment with a vapor space. When part of the liquid phase is removed, without removing any of the vapor phase, the gas-to-oil ratio increases. As more liquid is removed, the vapor space grows. The gas-oil ratio continues to increase. Now the sample with ullage space for transport has an altered composition from the original sample and will no longer be representative of the source. Based on these factors, it's not the preferred method for sampling liquid products. Next, let's look at the CVC using liquid displacement. Watch this illustration of how a CVC is used with liquid displacement during sampling. This method also suffers from the same problem that the evacuated cylinder method does in regards to sufficient vapor pressure to generate a vapor space and displace some liquid to allow for thermal expansion. This method does maintain the entire sample within the CVC, so the integrity of the sample is maintained. It does, however, require the user pay close attention to the volume of fluid displaced to ensure sample is not lost and that sufficient vapor space is available for thermal expansion. Now let's look at the CVC using liquid displacement with a dip tube. This is an illustration of how a CVC is used with liquid displacement using a dip tube during sampling. This method is almost identical to the other liquid displacement method. However, the addition of the dip tube allows the user to more accurately determine the ullage. As with the other two CVC methods, this one also has the same issue with low vapor pressure samples and generation of a vapor space. This method, performed properly, maintains the entire sample within the CVC, so the sample integrity and composition is maintained. Now we'll look at the FPC. This is an illustration of how a floating piston cylinder is used during sampling. This method is considered the gold standard for sealed sampling for 4 reasons. Number 1, the sample is fully contained and is never in contact with atmosphere or the displacement fluid, so there is no opportunity for loss or contamination during collection or handling. Number 2, the cylinder is built to have a gas-filled ullage space for thermal expansion when filled to 80% as directed. Number 3, the configuration of the cylinder allows the user to purge the initial sample, ensuring that only fresh sample is captured for analysis. This is important because the tubing connecting the source to the cylinder is filled with air prior to sampling. So as the product fills the tube, this air is compressed to the source pressure. When the cylinder is open to begin transferring sample, this air would be transferred with it. Understanding that air has a very high vapor pressure, any residual air can bias the results high. The venting procedure prior to moving the piston allows the initial air-contaminated product to be vented, so only fresh product will be captured. And lastly, number 4, most FPCs also have an internal mixer that allows the sample to be mixed prior to analysis. Lastly, we'll look at the manual piston cylinder. This is an illustration of how a manual piston cylinder is used during sampling. You'll notice this is very similar to how the FPC is sampled. As I mentioned, this is almost identical to the FPC except for the ability to control the position of the piston. ASTM D8009 was published for this type of sampling cylinder. This method is helpful for situations where the source pressure is very low, such as a tank sample that may only have head pressure available. The handle allows you to pull on the piston, which draws sample into the cylinder like a syringe. The piston O-rings are sealed against the walls of the cylinder interior, so they do require a differential pressure to get them moving. Sometimes the difference between the source pressure and the atmospheric pressure is not large enough to move the piston on its own. Generally, a little gentle pulling on the piston handle is sufficient to get things moving. Let's summarize what we've been talking about and rank the methods. The ideal sampling method is either the FPC or MPC methods. Next is the CVC using liquid displacement with a dip tube, and then liquid displacement without a dip tube. The least ideal sampling method is the evacuated CVC method. Now let's move on and have a look at hybrid sampling containers. As I mentioned earlier in the video, there is also a hybrid type of sampling container. I refer to it as hybrid sampling because it has elements of both a sealed sampling container and an atmospheric container. These are commonly referred to as composite samplers or proportional samplers. They are typically used for taking small incremental samples of large batches of product into a single container to capture a representative sample of the whole batch. This is intended to smooth out variations in composition from interfaces, etc. The image on the right is an example of what a CCQTA type composite sample container looks like. There are a few reasons I consider these hybrid. They are sealed containers, but they're not typically rated to contain source pressure like an FPC, MPC, or CVC. Once the sample is ready for testing, it goes through a homogenization step via a static mixer, which would introduce air into the system. Lastly, the homogenized sample is transferred to an atmospheric container for analysis and retention, therefore vapor pressure measurements could be impacted the same as for an atmospheric sample. Now just to note, there are fully sealed incremental samplers that utilize an FPC. These are commonly used for LPG or other high pressure products. However, these would not be considered a hybrid since the FPC is taken directly for analysis. Now let's move on to testing methods. There are several methods that are used for vapor pressure measurement. The most common of these are ASTM D6377, which reports as VPCRX at Y temperature. ASTM D5191, which reports as the RVPE or RVP equivalent. And ASTM D323, which is the original Reid vapor pressure method. Let's start with the original method, ASTM D323. It was developed in the 1930s for testing gasoline to avoid vapor lock in carburetor engines. Over time, the scope was expanded to include jet fuel, crude oil, and other petroleum products, but excluding LPG. This method utilizes fixed conditions that have become standard in the industry for decades. Most people in the industry are familiar with the term RVP. The test conditions are fixed volume sample and vapor expansion chambers, a fixed vapor to liquid ratio of 4:1, and a fixed temperature of 37.8 degrees C, and also requires atmospheric samples that are air saturated. The most significant drawback to this method is that it is intended for atmospheric samples that would be air saturated under normal conditions, such as gasoline in a fuel tank. The 4:1 VL ratio was designed to minimize the impact of air saturation on the vapor pressure measurement. This method has several procedural steps that involve contact with the atmosphere to ensure the sample is air saturated. As we've discussed previously, this provides an opportunity for significant loss of light end components and the reduction of the measured vapor pressure. For gasoline, this has less impact since the lightest component is C4. However, for crude oils that could potentially have volatile components as light as methane, it can have a significant impact on the measured result. This method has been mostly phased out of specifications in favor of newer methods. Next, let's look at ASTM D5191. This was developed as an automated vapor pressure method to remove some of the operator-related variability out of the manual RVP method. It was effectively a miniaturized version of the RVP. It is still commonly used for fuel specifications and some condensate specifications. However, the applicability for condensate has come into question recently due to the light end composition. This method uses the same conditions as the D323 RVP method. Similar to the drawback of the RVP method, this method also is intended for air-saturated atmospheric samples and includes the air saturation procedure for sample preparation for measurement. In the scope of the method, it is actually noted that it is not suitable for crude oils and to use ASTM D6377 instead. Moving on to ASTM D6377, you'll notice that the instrument photos don't change from D5191 to D6377. Although some legacy instruments were only suitable for D5191, most current vapor pressure instruments are capable of running both D5191 and D6377. This method uses the same temperature condition as the D323 and D5191 methods. However, it has provision for variable VL ratios. The VL range is listed in the method scope from 0.02 to 1 to 4 to 1. However, anecdotal evidence indicates that a lower VL limit of 0.2 to 1 is more practical. Also, the most notable difference with this method is the capacity to handle pressurized samples. This allows samples to be collected and measured at source conditions without contact with the atmosphere. Maintaining the sample single phase from the time of sampling through handling and analysis ensures results are representative of the source material. For crude oils, D6377 has quickly become the primary method listed in most quality specifications. Recent developments. The CCQTA recently published an advisory regarding 6377. The advisory was in reference to data presented that showed the measurement cell agitation rate could impact the reported vapor pressure value. This behavior is exaggerated at lower VL ratios where limited vapor space is available to be impacted by agitation. To summarize, without sufficient agitation, the method endpoint criteria could be met prior to reaching actual equilibrium with a low bias result reported. On this chart, the black circles depict the points where the method equilibrium criteria was met for each agitation rate. You can see that at lower agitation rates, the actual equilibrium was achieved much later than where the method criteria was met. This behavior has been noted specifically in heavy oil samples. However, there have been some reports of light oils having similar behavior. Work is currently underway with an ASTM Committee D02.08 to address the issue by revising the equilibrium criteria. However, that will take some time. In the interim, users are advised to consult with their instrument manufacturer regarding using the highest agitation rates practical without impacting the operation or sensitivity of the instrument. Understanding that the highest vapor pressure should occur at thermodynamic equilibrium, when comparing results, the highest results should be considered correct unless proven otherwise. If the measurement results are in doubt, confirm that the instrument is functioning properly and then repeat the measurement at different agitation rate. Let's summarize what we talked about today. We've gone through the various sampling methods, including constant volume cylinder or CVC, floating piston cylinder FPC, manual piston cylinder MPC, and finally the hybrid or composite sampler. Comparing each method, the FPC and MPC are shown to have the best ability to maintain sample integrity from source to analysis. We also compared three common ASTM vapor pressure methods: 323, D5191, and D6377. Of the three test methods compared, D6377 is the preferred method for vapor pressure analysis of crude oils. Thanks for watching, and I look forward to connecting again. If you'd like further information about this topic or any other topics the CCQTA is working on, please visit our website at ccqta.com. Thanks again. Please check back regularly for new additions to our Lunch and Learn series and other videos.